Hello everybody, myself Jyoti and this is fourth lecture of superconductivity. Yeah. Today what we are going to learn is what happens when magnetic field is applied to superconductor. So earlier it was assumed that the effect of magnetic field on a superconductor it will be same as the effect there on the metal. However, in 1933, Meissner and Oceanfeld measured what they did is they took tin sample and lead specimen and they cooled those samples below their transition temperatures. They kept the specimens in the magnetic field and then they cooled and they measured the flux distribution outside the samples. What they found that at their transition temperatures the specimens spontaneously became perfectly diamagnetic, cancelling all flux inside even though they have been cooled in a magnetic field. So, what is superconductor and what is resistance less metal? Whenever we talk about superconductor or think about superconductor, what we assume is superconductor, it is nothing but resistance less metal with zero resistance, but that is not true. This experiment was the first to demonstrate that superconductors are something more than materials which are perfectly conducting. They have an additional property that a merely resistance less metal would not possess. What is that property? A metal in the superconducting state never allows a magnetic flux density to exist in its interior. That means if you take the example or if you take the specimen of a superconductor, inside the superconductor magnetic flux density B it is 0. Whereas if you take the example of a resistance less metal with a zero resistance, in that sample the magnetic field it may be 0 or it may not be 0. So this is the basic difference between a superconductor and the resistance less metal. Now, what is Meissner effect? When a superconductor is cooled in a weak magnetic field, at the transition temperature, persistent currents arise on the surface and circulate so as to cancel the flux density inside, just the way as a magnetic field is applied after the metal has been cooled. This effect, whereby a superconductor never has flux density inside even when in applied magnetic field, that is called as Meissner effect. Suppose a magnetic field of flux density Ba is applied to a superconductor and we consider a superconducting rod with the field applied parallel to its length. An applied magnetic field of flux density Ba produces in the material flux density equal to mu r into Ba, where mu r is the relative permeability of the material. Now, metals which are other than ferromagnetic have a relative permeability, and that permeability value it is very close to 1. That is, you can take mu r equals to 1. So the flux density within them due to the applied magnetic field is equal to Ba. Okay. Now, however, as we have seen that total flux density inside the superconducting body is 0. So this perfect diamagnetism arises because surface screening currents circulate so as to produce a flux density Bi, which is which everywhere inside the metal exactly cancels the flux density due to the applied field. So we have there exists a magnetic field flux density inside, that is Bi, which cancels the applied magnetic field intensity Ba. So Bi equals to minus Ba, they are cancelling each other, and that is how inside the superconducting specimen we have 0, B equals to 0. So we have a superconductor where we haven't applied any magnetic field. It is cooled. Sorry, look at the figure B. It is cooled. After that, at low temperature, we have applied a magnetic field, and then we removed the magnetic field, and we applied the magnetic field and again cooled. So we are getting like this, and here the magnetic field is removed in the figure E. So what is basically happening? So A to B specimen becomes resistance less in the absence of magnetic field. In the figure C, what we are getting is magnetic field applied to a superconducting specimen. In D, we have removed it, and from E to F, specimen becomes superconducting in applied magnetic field, and then we have removed the applied magnetic field. Now we can describe the perfect diamagnetism simply by saying that for superconducting metal we have mu r 0, because we are not able to understand what we cannot describe it in terms of the screening current. Suppose we are doing it in terms of relative permeability. We are saying that mu r is 0. So that flux density inside, we know that formula is B equals to mu r into BA. If mu r is 0, B will be 0. Here we do not consider the mechanism by which the diamagnetism arises. The effect of the screening currents is included in the statement mu r equals to 0. The strength HA of the applied magnetic field is given by HA equals to BA upon mu 0, and the flux density in a magnetic material is related to strength of the applied field by B equals to mu 0 into HA plus M. This is the formula which you all know, must be knowing, because these formulas are done in earlier classes, where M is the magnetization or intensity of magnetization of the material. So the magnetization of a superconductor in which B equals to 0 must therefore be M equals to minus HA. So if I substitute here B equals to 0, I will get M equals to minus HA, and the magnetic susceptibility chi will be M upon H equals to minus 1. This is the maximum value for the susceptibility of a diamagnet. In the sense, a superconductor is a perfect diamagnet, whereas a resistance-less metal may not be. So, however, it must be noted that superconductivity is not only a strong diamagnetism, but it is also a new type of diamagnetism. Thank you. Thank you so much.